Funny, you can start.
Okay. Good afternoon, everyone. I am Panindra, a creative volunteer. Welcome to 142nd episode of Creative Online Weekend Talk. So, I'll be your host today. So, Creative is a community of like minded individuals driven by curiosity and creativity. As our name suggests, we believe in the power of creativity to fuel our active engagement with the world around us. With our tagline Knowledge Square, we embrace the ethos that sharing knowledge multiplies its manifold. Our vision at Creative is to foster constructive thinking across various domains. We are committed to exploring our non-textual, non-academic, and non-syllabus concept, enriching our understanding of the world in unconventional ways. Every Saturday, we gather online on Zoom and broadcast live on our YouTube channel to delve into the stimulating discussions and gain new insights. Today, we extend our heartfelt gratitude to all our resource persons who generously share their expertise and passion with us, enriching our collective learning experience. For today's episode, exploring cosmic origins, engineering insights into precision cosmology, we are glad to have S.K. Tripriya. S.K. Tripriya is a research scientist in the Electronics Engineering Group, Raman Research Institute. Specializing in RF and microwave engineering, she earned her M.Tech from the Indian Institute of Space Science and Technology and is currently pursuing a doctorate at the Indian Institute of Science, Bengaluru. Her early career involved significant contributions to wireless communication technologies, notably in the development of a millimeter wave system for an Indian 5G test bed at the Indian Institute of Science. Her expertise also extends to designing and developing reconfigurable MIMO antennas for cognitive radio applications. With 4 years of practical experience, Kirtipriya has diverse skills in antenna design, RF system design, optical fiber communications, and analog circuit designs. Currently, her research interests are towards the development of high sensitivity radiometers for cosmological applications, wherein her major focus is on designs, novel antenna designs, antenna analysis techniques, RF system designs, and high sensitivity system calibration strategies. Without any ado, let's give the stage to our speaker. Thank you.
Yeah. Thank you so much, Manindra, for the nice introduction. So shall I start?
Yeah, we can start.
Okay, I'll share my screen. Yes, screen is visible, right?
Yeah, it's visible.
Yes. So good afternoon, everyone. I'm myself Kirtipriya, and he gave a nice introduction to my work and my technical skills. But this talk, since I was told that the audience is going to be more general, I have actually catered the talk in such a way that I'll introduce a lot of these jargons. Which are generally used in this cosmology and radio astronomy, and then I'll talk about what work we are doing in Raman Research Institute and what experiments that I'm part of. And I'll also delve into the antenna design and the RF design, but it will not be like in depth, but I'll give an overview such that everyone can get an understanding of what's happening. So before I start the talk, I'd just like to acknowledge my entire team. So whatever I'll be showing in the forthcoming slides, it is not a single member contribution, and it's always the contribution of the team. So I thank all each and one of in this teams for their contribution to various aspects of the project. So moving on, before I start or directly go into the technical specifications of what I'm doing, first I'd like to give an overview of what are the projects that are going on in terms of precision cosmology in RRI and what I'm working on. So if we start with the history of universe, because that's where everything started, right? Today we are living in the Earth. There are a lot of stars, galaxies, sun, moon, everything is there in this universe today, but 13 billion years ago, the universe was not like that. It all started with a big bang, right? That's what we all know. It all started with a big bang, they say, the universe. But what happened after it? How have we transitioned into like the big bang which happened to whatever we are having now as Earth? how did this transition happen? This entire history of universe as to what happened and when it happened, this is like an open question still in cosmology, basically. So people are trying to research in this aspect, um, trying to understand. So there is an overall idea as to what would have happened. That's what I'm showing in the diagram here. But when it exactly happened, that's still an open question, which is what cosmologists are trying to answer. So if you start from the big bang now, big bang is like the explosion, you can imagine like that. Now after that, the universe has started expanding. So as the universe is expanding, and it's still expanding and accelerating universe that we are living in, so because of it, what happened was the universe temperature gradually started cooling. So during the big bang, imagine it's an explosion, so there is like a huge explosion with a lot of high temperatures are there. So there's everything is in the form of ions, plasma. But as the universe started expanding and cooling, now the plasma that was able to actually form some stable neutral atoms, because today we have hydrogen atoms, helium atoms, and we have these periodic table of elements, right? So there was a starting point to all of it, and that was the first elements in the periodic table, hydrogen and helium. So there was this formation of hydrogen and helium which happened somewhere around 400,000 years after the Big Bang. And that's what I've shown here. This actual epoch in the timeline of universe, it's called epoch of recombination. And this timeline is what Apsara experiment in RRI is focusing on. So Apsara is a ground-based telescope, and we are operating at 2 to 6 gigahertz. And this experiment is in a very nascent stage. We are now building the telescope, and we are doing a lot of R&D. I'll tell you why, we are still building it and what are the challenges involved in the forthcoming slides. But yeah, Apsara is one experiment which is ongoing, and I'm part of it. And it focuses mainly on the timeline early universe, when the first atoms in the universe formed. Now, once the first atoms formed, then for some time there was nothing happening in the universe. So that period is called dark age in the universe. And we still don't know, it's dark age because we still don't know what exactly happened in the universe at that time. Then, after the dark age, today we have all these galaxies and stars are there. How did they form? So, at some point of time, a first star or first galaxy seed point would have formed, and that timeline in the history of universe is called a cosmic dawn. So, from the cosmic dawn, then gradually the universe then transitioned into the universe which is there today, and it's a completely reionized universe is what we are living in today. So, from the cosmic dawn to what we are having as the ionized universe, there is this timeline called as epoch of reionization. So, this cosmic dawn and epoch of reionization, these are the two. Just one second. Yes, these are the two timelines in the history of universe that the other two experiments in RI is focusing on, which is Saras and Pratush. So Saras is a ground-based telescope which we are operating from 30 to 110 megahertz, and this experiment has been ongoing for more than a decade now. And Pratush is a space-based experiment which we are currently working with ISRO, and we are seed funded by ISRO for doing this, for constructing a payload, which will do this science from space. So these are the three major projects which I'm involved, and these are the timelines in the universe that we are probing. But when I say that we are probing the universe, what exactly am I doing? What am I looking at? So if we see, if we actually see the epoch of recombination, we are looking the epoch of recombination timeline by something called as cosmic microwave background radiation, and we are looking at this cosmic dawn and epoch of reionization periods by using something called as global 21 centimeter signal. Now, what are these two things? And I think I'll give a heads up that throughout the presentation, I'll be drawing parallels between both the experiments, and I'll be explaining the science behind them and compare them, so that you can get a feel for what exactly is happening. So, so the two probes which we are mainly using are the cosmic background radiation and the global 21 centimeter signal. So the global 21 centimeter signal I'll come to first. So this signal is emitted when the neutral hydrogen has a spin flip transition. I think it's again a jargon, but to understand it, we can just say that in a when the hydrogen atom has some excitation, it gains some slight energy because of some interaction with other electrons or atoms. It will again do a change in its flip and spin, and then it will emit a photon. So this, what you need to understand here is it's a signal which is coming from a neutral hydrogen atom, and it is emitted in frequency of 1420 megahertz. Now this signal is very important because this signal itself is giving us a lot of information to understand the history of universe. um, and if you see the cosmic microwave background radiation, it's a very interesting and important tool to study this universe, because this radiation of microwave background radiation, this is the oldest and faintest light that we can see in the universe today. And it comes from the time just after the Big Bang. Like I told you, the epoch of recombination happens at 400,000 years after the Big Bang. So this CMB radiation, it's coming basically from that time, which is like 13 billion years ago. And we are still seeing it, which itself is like, amazing, because you are seeing a signal which was emitted long back, and that is giving us a peek into what exactly happened in the universe. And one thing which you have to remember here is, even though they were emitted at 13 billion years ago, the universe has been expanding, right? So when these signals reach us today, they are actually redshifted in frequency, meaning they transition into lower frequencies. So for example, the CMB radiation, it was emitted in infrared frequencies, which is like very, very high frequency regime. But because of universe expansion, when it is coming to us today, it has reduced in its frequency into microwave frequency regime, which is microwave frequencies. When I say, you can imagine that to be your mobile phones, you have communication signals today. Those are all microwave frequencies, we say. So it is redshifted to that frequency when we are observing today. Whereas if we see the global 21 centimeter signal, it was emitted at microwave frequencies itself, that is 1420 megahertz. And when we see it today, it has downshifted to low frequency regimes of few megahertz, like 50 megahertz or 100 megahertz regime. So this is one important thing to keep in mind, because I'm saying here as 1420 megahertz, but then when we see later today, we'll be probing that in the 50 100 megahertz. Why so? Because the universe has expanded, so these frequencies have redshifted. So I'll also talk more about this cosmic microwave background radiation to understand what exactly that is. So as I told, initially the universe was like started with the Big Bang. Now what happened, if you see in this diagram over here, um, initially everything was there in the form of plasma. So even though photons were getting emitted, that is light, even though was getting emitted from various interactions that were happening, they were not able to escape, because they kept getting scattered off the ions, and they were not able to move freely. So the photons did not escape. But as soon as the neutral atom started forming, the hydrogen and helium, now there was more space. If you see in this atomic hydrogen I'm showing here, as soon as the neutral atom started forming, you have more space for the photons to travel. So they started traveling more freely. And the photons which were emitted during the time of Big Bang, they started traveling freely. And also there were photons which were emitted from the atomic hydrogen and helium formation itself. So all these photons, they started traveling towards us today. And this timeline, so if you see in this particular diagram, so after the photons started forming, the CMBs, once everything in the universe, when it became neutral, there were no more ions to get scattered off for the photons, so they started traveling more freely completely, and that's called as the last scattering surface. So the cosmic microwave background radiation what we see today is coming just from this last scattering surface, which happened like 400,000 years. And you know how it was discovered is by accident. And they won the Nobel Prize, I think in 1960s, they discovered this radiation by, this is Dr. Penzias and Wilson, they discovered this cosmic microwave background radiation by accident. They were actually building something else for a communication equipment, and they kept seeing something like a static which was occurring throughout in their data. And when they did all the calculations precisely, they always ended up with having some extra signal which had a temperature of 3 Kelvin. So that's how they found that this is. And parallelly there were astronomers who were actually trying to detect the signal, and they both collaborated and then discovered this background radiation. So but can we see it today in naked eye? I'm saying it's like a radiation, it's emitted with photons, but it's not light that we can see with our eyes, because it's emitted in the microwave frequencies. So we can't see it, but we can actually detect it using our antennas and RF systems, we can definitely detect it. So if you see in the sky today, we see, suppose you see the sky at night time, you have stars, you have moon. Then there is also the CMB radiation, which is there everywhere, because it's not like from a particular direction it's getting emitted at the source. It's there everywhere. It was emitted uniformly everywhere. So if I see the sky today, there is this faint background radiation, which is, if you imagine sky to be like this circle here, then it's uniformly distributed with a radiation temperature of 2.7 Kelvin. That's the CMB temperature. But this is the ideal case. But actual, if you see the sky, what will you see is there'll be a lot of these minute fluctuations in the sky temperature, in CMB temperature. And what is causing it is all the reactions which happened during the Big Bang. So all those photon interactions and ion interactions and then formation of hydrogen, everything will actually contribute to temperature fluctuations, which will change the CMB's temperature from 2.7 Kelvin by few millikelvin or microkelvin change. So this is one way people study the CMB radiation. They have antennas pointing to multiple directions in the sky, and they try to see the temperature fluctuations in the sky, which will give us information on what happened in the universe. This is one way to study universe. But there is another way which we have adopted. We are not adopting this method for our experiments. We are actually looking something at the CMB spectrum, we say. So what a CMB spectrum is, so I'm saying CMB is having a temperature of 2.7 Kelvin, right? So this temperature, if you consider this like a black body, everything associated with temperature has a radiation. I'll talk about it in the next slide to give an understanding of what is black body radiation. But if I see, suppose at multiple frequencies, how the signal is behaving, this is the graph of it. So this picture here, it is showing across frequency how the intensity of the CMB is varying. So this radiation has a peak at around 160 gigahertz, and this comes under microwave frequency regime, and that's how it got the name as cosmic microwave background. So if I see this signal instead of like different angles in sky, if I try to see it at different frequencies across, then with by seeing at the single position in sky, then I'll be seeing something like this. I'll get the power levels which are distributed like this. So this is how a CMB spectrum looks, we say. And so this is CMB spectrum, but how does our signal look? Do we have an idea of what we are detecting? How can I say what happened, 400,000 years after the Big Bang by seeing the CMB spectrum? So there are two different signals that we are trying to detect, as I told, because there are two different science goals here. So if you see the Saras and Pratush experiments, which are looking at signal from epoch of reionization, so this is coming from the 21 centimeter signal, global 21 centimeter signal, which is redshifted. And the problem with this is there are hundreds or thousands of possibilities of how the signal will look like. We just know that there have been computations by astrophysicists who say that these are the possible models because these kinds of reactions only would have happened in the universe. They have that understanding, and from that they have predicted that there can be like thousands of signals which are existing, which will tell us what exactly or how exactly the galaxies and stars started forming. And this signal here, you can see here, this shape, whatever I'm showing here, this they call it as the vanilla model. So this image below here, this shows the hundreds of possibilities which can occur. So the thing to note here is these signals are having temperatures in the order of millikelvin, and our CMB radiation, I'm saying it has Kelvin temperature, 3 Kelvin temperature it has. So these signals then are basically like 10 to the power of 5 times weaker than our CMB radiation. That is Saras and Pratush experiment. If you look at Apsara experiment, which is looking at epoch of recombination, this is looking at even farther in universe. Whatever happened almost 13 billion years ago. At least these Saras and Pratish experiments are looking somewhat in the near redshifts of, let's say, 1 or 5, which might be few million years ago. But Apsara experiment is looking at billion years ago. So the signal which we are trying to detect is something like this. These are called as quasi-periodic ripples, we say, and it has an amplitude of nanokelvin. Now, the main point to understand here is if our signals are this weak, then our system should be the system should have more sensitivity. So for the Saras and Pratyush experiments, we should have the sensitivity in the order of 10 power 5. Whereas Apsara experiment, we are expecting the sensitivity to be 1 part in 10 power 9. Which is very very challenging. I can say this is the sensitivity we want, but if you want to engineer a system which has that sensitivity, it will be very very difficult to do it, and there are a lot of engineering challenges associated in doing such an experiment. So before I move on to talk more about the exact challenges, I think now you will be wondering why I'm telling everything in terms of temperature. I'm talking 2 Kelvin, millikelvin, nanokelvin. Why temperatures? Because generally when you take any communication experiments, like if you have your FM station and you're receiving something in your phone, the FM radios, you say, oh, this much power was emitted, like watts, kilowatts was emitted from the source. We say like that. But here in astronomy, this you will see in generally in astronomy as such, everything will be in terms of temperatures. This was actually a new understanding for me even when I went to this field. But it kind of makes sense because let's just say you have a communication like FM radio, you know what you're radiating. You can, because someone is transmitting like some few kilowatts of power from one end. But in experiments like this, astronomy experiments, our sources are stars, sun, moon, let's say, but we exactly don't know what power is coming from them, but we can actually characterize them in terms of temperature. Every body which has a temperature will radiate. Even our human bodies also, we actually emit the radiation which is peaking in infrared. That's why your night vision cameras and all, if you see, how do they detect the human movement? They actually have like a thermal heat map from us. Temperature is getting mapped there into radiation. So like that, every body which has a temperature will have an associated radiation, which you can relate by this Rayleigh-Jeans law. So therefore, I am quantifying my power from the astronomical sources in terms of temperature because that makes sense. You can relate sources in terms of their temperatures. So if I use this equation of the black body radiation, I'll know what is the power that is coming from a particular source. And that is why I'm considering everything and talking everything in terms of temperature. And once I know the temperature, when it is received by the system, then I use some other formulation to convert it back to power levels of dB, dBm, whatever we conventionally use, by using this formula P equal to KTB. This is the formula which we use for converting temperatures into the power levels which are received by the system. Whereas the power which is emitted by the source, that will be actually calculated by this Rayleigh-Jeans law. So this is why everything in terms of temperatures, that's the background behind it. So moving on, if I just okay. So today, if you see sky at these frequencies of megahertz and gigahertz, how does the sky look? So the sky does not just have this EMB radiation, it has radiation from our own galaxy also. It's called synchrotron radiation, we say. So the synchrotron radiation is also very strong because if you see the sources of the CMB radiation is quite far away in the universe, whereas our galaxies are nearby. So they will have more power than the signal CMB signal. So if you look at the sky today at these frequencies of megahertz and gigahertz, the radiation which dominates is going to be from your own galaxy, which is synchrotron radiation. But the good thing here is we can model the foreground radiations by using a power law form. So that's what I've plotted here. You have this megahertz range. If you look at the temperatures here, they start at somewhere around 6000 Kelvin and they gradually drop and they continue to drop. And if I just see at the gigahertz regime, my temperature will vary like from 8 Kelvin to somewhere around 1 or 2 Kelvin. And but this is a good thing, even though they are stronger. The good thing is you can model them, because ultimately if you want to detect a nanokelvin or a millikelvin level signal, that's our science goal, detecting these millikelvin nanokelvin signals. And if I want to detect that, I should be able to separate this foreground and the signal. The two should be separated. So there should be some property which I can use to separate them, and one of them seems to be this foreground radiation's power law form, which we can use apparently to separate the signal and the sky. So the problem here is it's not that easy as it seems. because if you see the power levels, now this is in temperature. Now I'll come to the terminologies which everyone is maybe used to. Power levels. If I see within this megahertz band how much power is received, the power received is in the order of minus 95 dBm or minus 110 dBm, which is again a very, very low power. And in the 2 to 6 gigahertz, it's even lesser. It's around minus 110 to minus 120 dBm. So the challenge itself is the power from the sky itself is very less, and we are trying to look at something which is even fainter than this foreground sky itself. So we have to use some special techniques, therefore, in order to separate the signal and the sky. So, what are the challenges, therefore, again is one is the strong foreground versus the weak signal. So, our signal is just millikelvin level amplitude at low frequencies, which means, and you look at this, our signal at low frequencies are in 1000 Kelvin, which translates to like 10 to the power of 6 times weaker signal. So, that's one main challenge. And next is the radio frequency interference. I mean, I can understand the development has to happen everywhere, and everyone wants mobile communication signals. You want to communicate with people. You can't imagine, living without mobile towers around you. But these things are actually a challenge for our experiments, because mobile signals, what do they do is they are very strong when they are radiated. So they are very powerful. If you see here in this plot, the radio frequency interference in Bangalore I'm showing. Um, in gigahertz regime, that's where mainly your 4G, 5G, 3G, everything is there. So we can't really do any science here because the entire band has a very powerful signal. So these are at the power level of minus 40 dBm. And our sky, if I'm seeing, just the sky is minus 100 dBm. So these signals are already 60 dB stronger than the sky. And but I don't want these signals. I'm trying to look for some signals which are even weaker than the sky. So generally our RF systems will have like lot of gain or amplification first of all to amplify this weak sky. And these 5G signals, 2G signals from mobile towers, they'll saturate or damage our systems easily. So therefore, they actually are a challenge for us, this RFA situation. Excuse me. So therefore, it becomes very challenging to do any kind of experiment in cities. So we don't carry out our experiments in the cities or nearby towns where it is population is more. And if you notice, most of the experiments in radio astronomy in this community, it will not happen in very popular area. It will happen in some desert like Australian western outback areas, or in US also, wherever there are deserts and there are no one around that area. That's where these experiments will happen, because what people consider as development, these telecom signals, FM signals, they are detrimental for doing this astronomy science. So they are a major challenge actually. And also again, um, generally if you take the system itself, your how do you design the antenna and then your RF system, your digital system, such that they don't also interfere with your signal separation. So all these we call it as systematics. So engineering the systematics to be less is also again a challenge. So I'll talk about the first thing, RFI. This might be interesting for you all. So how do we tackle the radio frequency interferences which are there? Well, we don't. We actually run away from them. That's the only thing we can do. So what do we do here is, we go to the remotest of locations. We first do, before we start any experiment, we always do an RFI survey in any location. So, for example, in Bangalore, when we did, we saw all these 4G, 5G signals coming in. But then we have our observatory in Gauribidanu. So when we went there and we did this RFA survey, we saw that at least in the gigahertz regime, surprisingly 4G signals and 5G signals were not there. So we got a free band from 2.5 to 5 gigahertz, which we think we can use it for doing some science. But apart from Gauri Bidanur, we have also explored areas like Hanle, which is in Ladakh, and then Tamchungiri, which is again in Ladakh, and it's slightly farther away from Hanle. These again, Hanle is an observatory in Ladakh. Very nice place, which is it's exactly been earmarked for doing the astronomy science, and it's also one of the India's only dark sky reserve. You can Google it and see. It's a India's dark sky reserve, they call it. So we went there, we did some testing, and that area gave us a very clean data. That's what you see here in the left side. So this is the data which we got from Tamchungiri RFI, Tamchungiri location. You see that there are no mobile signals. Mobile signals are not there. Then the only signals which we saw were the satellite signals, which are okay because they are of lower power and we can manage with whatever they are throwing. So the satellite signals are the only thing which we saw at the gigahertz regime in Tamchungiri. And this plot is showing the comparison of the various locations. And as also part of recent Arctic expedition from India, one of our team members, he traveled all the way to Himadri in order to do Himadri is the Arctic station, which is India's Arctic station basically. So he traveled all the way to Arctic and then he stayed there for 2 weeks and then he did a survey to see if we can actually go back there and do some science. And he did this RFI survey for both the low frequencies and high frequencies. And high frequency, it was very clean out there. There are no signals, even the satellite signals were less there. So, but logistics are very difficult if you want to go to Arctic to do science every time. So, currently, we have chosen, therefore, Ladakh as one of the suitable sites for doing these Apsara experiments. And already, Saras, they have been going on almost a decade for various remote places in the country. Recently, now as I'm talking, a team is currently in Andaman and Nicobar, where they have identified a remote location. Last year, they went there for an RFI survey, and then this year they have gone back again to do science. So our experiment is basically a deployable system we have made. It can be taken everywhere because it has only one antenna. It can be taken anywhere, and then it gets deployed in any location. So a team has gone with with our whole experiment to Andaman. They'll be staying there for again 2 weeks, and they'll be doing some observations, and they'll be coming back with the system. And that's the mode of operation for these experiments. So now I'll move on to slightly technical topics, like what do we do in the antenna design and how do we cater to our RF system design, so that we can minimize whatever is our own system's contribution into this data. Because at the end of the day, you receive something and then you do all the processing, and then finally you find out that it's not the signal but it's something coming from your own antenna. That will be really bad. So we have to engineer our antennas and RF systems in such a way that you minimize its own contribution to these spectrums. So this is a model of, this is actually not model, this is the actual Saras antenna which is deployed on water. So we are currently deploying our antennas and systems on water. We have moved away, it's called ground-based experiment, but we have moved away from that and we have started exploring water as a base for our experiments. So we are currently deploying all our antennas and systems on water for Saras. And this is exactly that cone, whatever you are seeing on the water here. So that's the Saras antenna that is deployed on water. And how do we design our antennas? What are the guidelines which we follow? So what happens is if you put an antenna towards sky, the antenna will have its own radiation pattern. Radiation pattern, you can understand it as the directions in which the antenna will have like a maximum gain. So it will have a certain pattern associated with it. Each antenna has a different radiation pattern. So the sky will be like weighed by the antenna according to its radiation pattern, and then you multiply it with the impedance matching of the antenna towards next step into the system. So after doing all these things, we get some TA here. This TA here is the antenna temperature, which we call. So this antenna temperature, we have certain guidelines for this. This antenna temperature, whatever we are getting here, it not only has the foreground sky, it also has the information what we are looking for embedded in it. So we have to make sure that our own antenna doesn't contribute to or distort this embedded information, right? So the guidelines what we follow is we make sure that our antenna is it has no beam dispersion. What do we mean by that is our systems are basically broadband systems. We start at 55 megahertz and we go to 110 megahertz, or we start at 2 gigahertz and we work till 6 gigahertz. These we call as broadband systems. So the antennas, whatever we have, they should actually have the same radiation pattern at all frequencies. That's very important, because if suppose the radiation pattern is different at different frequencies, imagine that sky will get sampled differently at different frequencies. So the signal what we're looking for, it has a particular shape across the spectrum. And if our antenna also has a similar shape, then we can't detect the signal. It will hinder the detection. So one main design guideline which we follow for the antenna is it to be achromatic. The other thing is, so I think this again might be a jargon for those who don't know this return loss of the antenna and all. But you can just consider that. So this is how the sky will look at the gigahertz regime. Now, if my antenna's return loss also is engineered to be having this shape, then I can separate the foreground and the signal easily. But if my antenna's return loss has like ripples, or it has resonance dips, or it has some funny shapes, then that will get multiplicated into this and it will distort the signal which you are looking for. So these are some of the design guidelines which have been following for the antenna. And so if you're someone who's familiar with antennas and broadband antennas, you will say that, oh, I can use a horn antenna directly. They are broadband. They'll not do anything. If you think in that way, so we did an analysis to see whether we can use these standard ultra wideband antennas. So we have our own pipelines. What we do is whatever is there in the practical environment, we try to emulate it in our pipeline. So we take the antennas measured or simulated characteristics of these return loss, radiation pattern, everything. We put it into our software, which we have written. And it also takes the sky. We can actually get the sky maps also, which are available from the measured. So there are a lot of satellites which have measured the sky and its frequencies, and what are the power levels at various frequencies. These are available online as a free source. So we take that and then we put it into our software. So now what we do is, whatever is this mathematical equation that I am showing here to calculate the TA, we basically do that in our software, where I'm taking the TB as the sky from the measured sky maps, and G here is taken from our own antenna, whatever we have simulated. And then the entire thing, mathematics is going on here. And finally, I get a TA spectrum. And that TA spectrum, if it's smooth, I try to fit that with a smooth function. So basically, there is if suppose my understanding here is that if I have a smooth TA, I can fit it with a known function, and I can subtract the functions, and I'll get something called as a residue. And the residue will tell me whether the whole pipeline or the antenna is suitable for doing the science. So, for example, you can see that I've taken this horn antenna, I've taken this Vivaldi antenna. These are the return loss characteristics. Now, if I put it in my pipeline, I am getting residues which are in the order of millikelvin, not millikelvin. These are actually zero point 0.3 Kelvin or 1 Kelvin temperatures. This is the residual RMS. But if suppose I take an ideal antenna which follows all my guidelines, then I will actually get a residue here. You see this ripple here. This actually has a residue of the order of nanokelvin. So if my antenna is good and similar to an ideal antenna, I can actually get a residue of order of nanokelvin, which means my antenna will detect a signal of nanokelvin amplitude. If not, if I use the horn or these things, I'll be getting 1 Kelvin residues and I will not be able to detect the signal. So that's why we don't use the conventional antennas which are available in market. We design our own antennas according to our design guidelines, such a way that we can minimize these residues as much as possible. So these are some of the antennas which we have designed for Saras, Pratyush and Apsara experiments. So the Saras antenna, as I told, is currently on water. So this is the antenna. This cone which you see here is the antenna part, and it's floating on a raft. And the Pratyush, as I told, is for a space based experiment. So this is our antenna currently, and all the payload electronics will be sitting inside the antenna reflector. And Apsara is again in a different frequency range. Now, the one thing which you can see is the low frequency antennas are quite big. You can see it, I think they'll be of the size of 1 meter or so. Whereas if I move on to high frequency, my antennas become smaller and smaller. That's why, you know, in your phones and all, you have your antennas to be very small because you're operating in gigahertz regimes mostly. So therefore the antennas become small. That's one advantage for us. It's easily carryable. uh, it's of maybe 14-15 centimeter size. That's the size of this antenna what I'm showing here. And all these antennas we have actually meticulously engineered them to follow these design guidelines. It's very challenging to make them follow these achromaticity design guideline because we are hitting the physics limit there. You know, it's very difficult to design antennas which are more than 1 octave bandwidth, we say, which can have the same performance at all frequencies. That's very difficult to engineer. But we have tried and we have achieved millikelvin level sensitivity so far in all our antennas. So for Saras and Pratush, that sensitivity is enough. We can detect the signals which are millikelvin level sensitivity with these antennas. Whereas for Apsara, now we are trying to improve the sensitivity further and go to order of nanokelvin or microkelvin at the best. And we are exploring new techniques to do these things. So this is in terms of the antenna perspective. This is the overall overview of the antenna, what we designed and what are the guidelines we followed. But if you just see in terms of the radiometer itself, how do we then? So from the antenna, the signal has to go through some system. It has to get amplified, filtered. Then it has to go to the digital systems. It has to get processed, and finally we'll get some data. And there are a lot of electronics involved between the antenna to the final output. And all these electronics we categorize as the RF systems and the digital systems. So I'll be mostly talking here about the RF system chain because that's where I work mostly. So for the RF system chain, now what are the challenges when you try to build an RF system? The first thing is these systems should have more gain because our signals from sky are of very low amplitude. So I have to amplify them first of all. And other thing is RFI interferences are there outside the band. So let's just say in Gauri Budunur I have a free band of 2.5 to 4 gigahertz. But outside of 2.5 and 4 gigahertz, there are other signals. So if I use my system to amplify uniformly at all frequencies, then the out of band, that is the frequencies at 1 gigahertz, might destroy my system. So I don't want the 1 gigahertz powerful signals from destroying the system. So I basically use some filters therefore. So these are some of the things which we use to build our system, having more gain, having filtering. But the other important thing is generally also when we talk in RF, one thing which is very important for any RF system is impedance matching. So we have to have maximum power to be transferred at every stage. We don't want most of the power to be dropped somewhere or power to be dissipated as heat. We want all the power to get transferred from antenna to the digital systems. For that, impedance matching is very important. But sometimes what happens is you can't perfectly impedance match any system. There will be impedance mismatches. And because of impedance mismatches, what will happen is, let's just say now a signal is coming from antenna, it goes to the system and then it gets reflected back and forth because of this impedance matching. And these things, these back and forth reflections, they cause something called as standing waves. And these standing waves, unfortunately, they are like these ripples actually, which will mimic our signals, whatever we are looking for. So instead of looking for our signals, we'll end up with some systematics from our own system if we don't do this impedance matching carefully. But doing impedance matching at all frequencies perfectly, it's very challenging. So therefore, we have to take some calibration strategies where we remove the system's response itself from our final spectrum. So for example, I can show you some of these. So these are pictures from our own systems and runs, whatever I've done. So for example, in our system, as the signal propagates towards the digital, suppose at some point of time there are reflections as I told. You see here my final data, the systematics due to poor reverse isolation I've written here. So this kind of ripples occur in the data. And this is having a RMS residual of zero point 0.7 Kelvin. So your final thing will be limited at zero point 0.7 Kelvin. You can't reach millikelvin. So this is one kind of systematics which are occurring. And if suppose there are no systematics, our SARA system has achieved that, and it's one of the best radiometers in the world, and they are like doing forefront science. and they are actually having residuals in the order of millikelvin, and that's what we also need to detect a millikelvin level signal. Our residues should be millikelvin level, and this is the ideal case which we have achieved also in our lab with our Saras systems. um, the other thing is, as I told, RFI also. It's not just the antenna which picks up RFI, but you can get RFI from various parts in the system. So, suppose this is one diagram which shows that this sudden spike which is appearing here, this can be coming. This seems to be coming from our own digital system sometimes, because there are clocks in the digital systems, which again is problem for the RF systems. So these things create these sudden spikes, and these sudden spikes will again limit our detections. So this is like meticulous engineering is what we are trying to do here. It's not just we build some system and then we put it and make it work. It's more like we keep understanding how our system works. We have to understand each and every component and its contribution to the system. So we are doing more like a meticulous engineering here. So this is the RF system architecture which we are following. So as I told, how do we eliminate the systematics from our own RF systems and digital system is we have something called as a calibration procedure. And what do we do here in the calibration is, so this is the antenna here, and antenna signal passes through the system once. Here we have a switch, if you see. And this is a very standard technique in radio astronomy. It's called as a Dickey switching radiometer. What we're doing here is the signal is constantly getting switched between an antenna and a known noise source. So we have a known noise source and then we have an antenna, and we keep switching between them, maybe in 1 second cadence, let's say. So we'll have like a set of equations at the end of all these things, where we can use those equations to cancel out the systematics itself. So this is called as a calibration procedure in our system. In our system, we have two different types of calibration. One is a bandpass calibration, and then there is this absolute calibration. So the bandpass calibration, it helps us in removing the gain fluctuations in the system. The absolute calibration is another, it's a different thing. What we are trying to do in absolute calibration is, so after putting the antenna signal through our system output of the digital, we'll get the output not in terms of voltage or power, we'll get it in terms of ADC counts, because digital system will throw you something. How do you map it? How do you map what is the ADC count to what is the antenna power that is received? So that mapping has to be done somewhere. So that's what is done by this absolute calibration to convert the digital spectrum units into temperature scale. So these are the two types of calibration which we do. And this is a model of our RF backend system. And in the RF backend system, what we do again is again one more switching. And one thing you can see here is we have divided our system's power into two channels, and we have two channels. The same signal is fed in two channels. This kind of architecture helps us in reducing the additives or systematics coming from our own digital systems. So this has been carefully engineered, all these architectures. I mean, the Dickey radiometer is a popular one, but we have modified the Dickey radiometers, and even the backend system architecture has been carefully engineered such a way that we can minimize the various systematics, and that's what makes our systems very different also from all the other world class systems. So there are other competitors around the world who are trying to do similar science. There is a team in US who's trying to do it. Then there are Europeans also who are trying to do it. But ours is also, our Saras system. After so much of experimentation with these systems, we have actually proved that out of those hundred thousands of signals which are possible, at least 20-30% cannot occur. We have proved, and this has been published in Nature also. Using the system, we have at least achieved doing that, and also now hopefully with our next runs or observation which is currently happening in Andaman, we can actually disprove some more, or we'll be able to detect the signals soon, we are thinking. So that is in terms of Saras and Pratyush, we are already there doing that good science. But for Apsara, if you see, the sensitivity which we want is nanokelvin, but then we are currently there, maybe at millikelvin level, we are trying to build the systems. But how do we reach the nanokelvin? What the science that we can do? Because directly building nanokelvin level sensitivity is very, very difficult. So the principle which we follow here is, the more you observe and average your signal, your noise comes down. That's a standard thing. Noise goes down with averaging. And so this is the standard sensitivity of the radiometric calculation. So if I want my RMS here to be in the order of millikelvin, then I can take a system which is having a noise figure of 77 Kelvin or 1 dB noise figure. And if I do an observation for 1 day, then I can reach the millikelvin level sensitivity. But look at high frequency systems for gigahertz Apsara. If I want to even achieve a microkelvin with the same noise figure of the system, I have to do observation for 2900 days, which is like very challenging. How do you do observation for such a long time? So then what do we do here is, other thing is, we are trying to cool our systems now for Apsara. So therefore we have now ventured into cryo cooling. We are building our own cryostat, and using the cryostat we are planning to cool our electronics, so that if you see here, if instead of 77 Kelvin, if I have a 10 Kelvin cooled receiver, I can actually achieve the microkelvin sensitivity in somewhat lesser time, 1100 days. But still, 1100 days is also too much. Then what do we do? Then we can actually scale the number of antennas. Instead of having one antenna, if I have hundreds of antennas, then I can achieve the same sensitivity in 11 days, which is quite possible. So therefore, Apsara experiment is now trying to build like an array or hundreds of antennas, which can observe for these longer time, but have also has like a very low noise temperature of around 10 Kelvin or so. So therefore, we are having cooled systems. We are trying to build arrays, and the experiment we are just started doing one antenna system right now, and we are slowly getting towards gradually planning to build up the sensitivity towards this microkelvin. So this is our Saras system, whatever we have right now. And this is a system which also has been deployed in various locations, and it has recently gone to Andaman also. So this is the antenna, and below the antenna sits our RF front-end electronics. And from the RF front-end, this is what our RF front-end electronics is. On top of it, antenna gets mounted. So from here, the signal then goes to RF backend through optic fiber cables. We are currently using optic fiber cables for that. So the RF backend electronics and the digital, they are actually housed in the lake shore itself. They are not on water; they are there in the lake shore on the ground. So the signal goes to the RF backend. From RF backend, it goes to our digital spectrometer, which gets process the data and then stores it in our laptop. We have a laptop which automatically acquires the thing. So all these things are automated also. We just go there, we set up all these things, we give the run, it observes continuously for 8 hours. We go back there, we take the data out, we process it. That's the work mode. So I can't show Pratush and Apsara. Apsara is more in nascent stage. We are still building. And Pratush, since we are there in talks with ISRO, I cannot show that system to you right now. But this is our Saras, and this is how we have been operating. And with this, I'll conclude my talk. I hope it has been interesting for you all, because I've tried to talk more in terms of layman terms, and I've tried to minimize the jargons for you all. And if you want to know more on this, our lab activities, you can visit Distortion Lab Activities website. And the ongoing research activities are related to antenna design, then cooled and uncooled receivers, wideband system development. We even work on the pipeline development. So we are looking for mix of students from all backgrounds basically. So these are the opportunities which are there in the distortion lab. Currently we have something called as visiting student programs, which we are open for any undergrads who are currently pursuing anything, any background in BSc physics, electronics, BTech. So we have a lot of work related to antennas, analog electronics, RF systems, digital systems, even the data science pipeline. So whoever is interested, you can write to me, or you can write to professors whose mail IDs you can get from the website. And finally, also we have some more longer term questions of research assistants. So these are the modes we are currently taking students. So with this, I conclude, and thank you all for your time, and I'm open to take any questions.
Thank you, ma'am.
Yeah.
And unmuting everyone. You can unmute yourself. Okay. Any question? If any questions, you can unmute and ask the question. Okay, I think no questions, ma'am.
Okay.
Okay. Okay. Thank you very much, ma'am, for this session and for insight knowledge. Thank you very much for accepting our invitation.
Thank you so much for inviting.
Thank you. Thank you, ma'am.